Thanks a lot, Vivek. Can you hear me? And can you see my screen?
Yeah, we can hear you and see your screen. Please go ahead.
Okay, thank you. Yeah, so thank you very much for this opportunity. And thanks, Vivek, for uh, explaining the significance of Giordano Bruno's thinking and work. Uh, it's a particular pleasure for me to give this talk. I read about Giordano Bruno as a child and was fascinated by, although very depressed also, but I was fascinated by that story. And so it's a particular pleasure to give this talk that is leading up to Bruno Day that we all observe. So here is a portrait of Giordano Bruno, which I believe is as authentic as it gets. And 300 years after his death, uh, a sculpture in his memory was erected in the spot where he was actually burnt at the stake. So, as Vivek said, he led this extremely interesting life. And at some point, he made the statement that stars are other suns with their own planets, which, if you think about it, is a huge leap uh, in thinking that he did in the 1600s. So he said stars are other suns. He said stars, therefore, could have their own planets. And he said that planets could harbor life. So, to come back to today's theme, what is universal about the universe? Uh, as Vivek said, there are many meanings of that. I also very strongly recall the slogan that our friend Sabyasachi Chatterjee coined for the International Year of Astronomy, namely universalizing the universe. At that time, the theme was to bring our understanding of the universe and the excitement associated with that to everybody. That was the theme of the International Year. It was the theme of AI Pearson's work as well, and what that would mean then to our daily lives. But here, what we are thinking about a little bit is this idea that we can understand the phenomena observed in the universe based on the physics understanding that we gain on Earth, in laboratories, in observations, in testing our hypotheses on Earth. And if you think about it, it's this is a huge leap actually, because the universe is, as we know, enormous, mind-bogglingly large, and it is a leap of faith to think that whatever we uh, know based on our experience on Earth and based on observations and testing hypotheses on Earth will apply everywhere in the universe. But that is sort of the idea of what is universal about the universe. And embodied in this idea is a sort of rejection of exceptionalism. And we can see that around in the thinking of people around the time that we're talking about. So a few decades before Giordano Bruno, Nicholas Copernicus had proposed the so-called heliocentric theory of the solar system, which went contrary to the understanding in Europe at the time. And essentially, it was rejection of the idea that the Earth is exceptional. So it's a rejection, started with a rejection of exceptionalism. So Bruno also uh, came to the realization that just as the Earth was not exceptional in the solar system, the Sun was not exceptional in the cosmos. However, empirical evidence in support of Bruno's idea had to wait a long time. So the first planet around a star that is not our sun was discovered in 1992. And this was a star that was very unlike our sun. It was a star that is known as, it was an example of what we call pulsars, which are extremely strong magnetized stars. So they are much stronger magnets than our own sun. Our sun is also a magnet, but pulsars are much, much stronger magnets. And they spin, and usually the axis around which they spin is different from the axis of their magnet. So, what effect? I mean, these kinds of stars were actually discovered in 1967 by Jocelyn Bell. That's a fascinating story in it.
Rajulji, your voice stopped.
We can't hear you, Prajwalji. I think there's a network issue at your end.
Cannot be heard, Prajwalji. We cannot hear you. Richa ji, please remove all who are not Indian name.
Mm,
I
Runabada,
think
this.
some problem is being created.
Okay, okay. Maybe if someone can get in
Looks like
touch.
the host and those who are there in the host, co-host or co-host, their mic activity is not shown. Otherwise, please, ma'am, you disconnect and rejoin once again. Sometimes problem may get altered. Say some people, they do not know put their names. They are putting the name of the phone, which is not a good practice. Please express yourself.
Can someone talk to Prajwal because Prajwal is still logged in, but
Yeah, I tried to call Prajwal on the line, but it's ringing. She's not taking the phone. I sent her a message WhatsApp, and
এর জন্য প্রথমে ব্যাংক অ্যাকাউন্টের নামটা লিখে দেবেন, ব্যাংকের নাম।
Yeah, I think Prajwal is logged out. You log back again. I called her, didn't get through. I also sent
Yeah,
her an email and a
she
message.
knows everything, and
Yeah. I
she's, I
sent her
think,
a message and a WhatsApp and a
yeah.
phone
I
call,
have also
email.
called, but she didn't
Yeah.
take the call. Uh,
Yeah, Vivek, you're there.
I'm here.
Yeah, maybe you can just briefly
Okay.
tell a little more about so that we can, people are there, they'll be wondering what happened.
yeah, and the
Okay.
recording is also in progress.
So while we are waiting for Prajwal ji to come and continue the presentation, let me say a few words about why AIPSN.
May-
Okay. Waiting for Prajwal ji to come back in this meeting. I think let me briefly say a few words about why AIPSN has considered it important to observe this day, 17th February, National Day of Astronomy, and also to commemorate will be another program on the 17th, a lecture by Dr.
Priya Hassan.
And she will be speaking on the findings, very important and interesting findings of the large telescopes, which have now started functioning. So this year we have two programs. One is this lecture, which has been interrupted by Prajwal on what is universal in the universe. And the other one is the lecture on the 17th. Dr. Priya will be delivering that, and that will be chaired by TV Venkateshwaran. For us, Giordano Bruno is really a iconic person who made a number of very important and very seminal contributions to the kind of work that we are doing. Firstly, he asserted that the work of Copernicus about the heliocentric solar system, that is correct. At that point in time, it was not universally accepted. As you know, a few years later, Galileo again was punished for asserting that, but Bruno asserted that. And he said that not only do the planets and this Earth go around the sun, but in addition, all those points of light that we see in the night
Vivek,
sky.
Prajwal is
Yes.
back. Prajwal is
Okay,
back.
good. Prajwal?
So, at what point did you lose me?
About the third slide or so. When you're talking about the
Okay.
pulsars, after the pulsar.
You talked about the first exoplanet around the pulsar. That was when we lost you.
Okay.
Okay, so continue from there.
Can you hear me now?
Yeah, we
Yeah,
can hear.
yeah,
Okay. So, did you see this slide?
yeah. Up to this slide.
Okay. All right. So the next planet that was discovered was 3 years later, and it was a planet around the star called 51 Pegasi. And you can still hear me, right?
Prajwal, maybe because your bandwidth is low, if you can switch off your video and we can just focus on that.
My bandwidth is not low, actually. The bandwidth is fine. Uh, okay. I've switched off the video. Can you hear me now?
Yeah,
We can hear you. Yeah.
Okay.
we can hear you.
Okay. Can you see my screen?
Yeah.
Yeah, yeah.
All right. So the next planet that was discovered was around this star called 51 Pegasi. And this star uh, was a regular star, not a magnetized star. So the method that was used to discover the planet around this star was slightly different from the method that I described earlier with this magnetized pulsar. To describe that, I just wanted to talk about what Fraunhofer lines are, which we see in our own sun. So this slide is showing uh, the disk of the sun, and this is a real picture which shows the sunspots and so on. And we know that when the sun's light is stretched by something like a raindrop or a prism, then we see a rainbow. Now, if that stretching is done to a large extent, then in addition to the rainbow like feature, we see dark, very sharp lines across the spectrum. And these are called Fraunhofer lines. And the reason we see these lines is because the outer layers of the sun is at a somewhat lower temperature than the inner part of the sun. Both are at very high temperatures. So the outer part is somewhat lower than the inner part. And therefore, the atoms in the outer parts of the sun absorb some of the light that is from the inner part at specific wavelengths, depending on what those atoms are. So we're basically seeing the imprint of the elements that are there in the outer part of the sun in the form of these dark lines. And it's actually very easy to see the dark lines. We can see them using a CD. And our friend Arvind Gupta, as many of you know, has designed a way to see these things, these lines using the CD and the spectrum of the sun. I mean, not just the spectrum of the sun, it could also be pointed at a tube light or any source of light in our vicinity also to tell us what the spectrum is like. And I'm just showing you a very beautiful manual that was written by a young student called Nainika Ghosh to describe how to construct such a spectrograph, which I can share with anyone if you like. And so now, can someone tell me if you can see my cursor? Can you see a green cursor which I'm pointing?
Yes, ma'am.
Okay, so imagine that this is a star. Imagine that this is 51 Pegasi. If it has a planet around it, this is how it would move. And what is shown at the bottom here is how we would see it if we were looking at it in this plane, that is, in the plane of my screen. So now, if you think about it, we have the capacity to only see this sun because that is the one which is glowing. We cannot see the planet because the planet does not glow. However, because the planet is orbiting around this sun or star, that affects the motion of the star and the star moves. So now, if we are looking at the front of our lines from this star, because of the Doppler effect, these lines will keep shifting. And that is what is shown here. So you look at this bottom diagram, which is a representation of the rainbow spectrum from this star. And if it has a planet around it, it will wobble. And so these black lines, the front of a lines, will keep shifting to the right and to the left. And that is what is plotted here on top. So one can, from the Doppler shift, infer the speed, and one can plot the speed, and you get this kind of very regular curve from which you can infer that there is a planet around this star. And one can even derive the mass of the planet. So this is how the planet around Pegasi 51 was discovered, and several such planets were discovered after this. And this was actually a Nobel Prize winning discovery. And then there was a telescope called Kepler, which was launched. And that was launched for the specific purpose of detecting planets and has detected about 5,000 planets, around about 4,000 stars. The way Kepler detects planets is somewhat interesting. It's again a little different. So the way it does it is that you have to imagine a star like our sun, but very far away. So we cannot see it as a disk, we see it only as a point source. And imagine there is a planet around it, which is orbiting it such that the planet comes in front of that star and then behind it, in front and behind, and so on. So that is what is shown in this sketch. So the sketch shows you a planet around this, orbiting around the sun. And so now the planet is coming in front of the sun, and now it is going behind. So the point here is that we can measure the total light from this star. And when the planet comes in front of it, it is eclipsing the star to a very small extent and hiding some of the light from the star. And so therefore, we will see a reduction in the light that we measure. So that is what is being shown in this graph here. You can still hear me, right?
Yes, yes.
Okay. If you lose me, please call me on my phone so that I know. So by measuring the light from these stars and seeing how the light changes, and when the light changes, or if the light changes, seeing what is the behavior of that change, and does it behave in this fashion, uh, the Kepler team was able to discover many, many, many planets around many thousands of stars. And there have even been some stars that have shown multiple planets. So this is a representation of one such system. It's called the TRAPPIST system. And this is only an illustration. These are not real data because, as I said, we are not able to see the planets. The planets don't glow. We can only infer their presence by measuring the amount of light that comes from their star and seeing how it changes and whether that change, the pattern of that change, matches with the pattern of an eclipsing planet. So the empirical evidence in favor of the hypothesis that Giordano Bruno put forth is now just overwhelming. And this is a very hot area of research. And more recently, you may have heard about the James Webb Space Telescope, which has been launched to image the cosmos in infrared light. And with the James Webb Telescope, not only can planets around other stars be seen, but signi-
बघू माझ्याकडे दाखवते दूरदर्शन लावते ना मी याच्या आधी बाळा मी बघितली
not only can the planet's uh, path be measured, but even the signatures of the planet's atmosphere can be measured. And that's represented in this diagram here. So you can see here that suppose you imagine that this is a planet moving around a sun. Let me find my cursor, just one second. Okay, for some reason my cursor is not visible, but you see the diagram of a sun and the planet moving in front of it. Around the planet, they have represented its atmosphere. So there is a very short interval of time when we see the light from the star through its atmosphere, and the planet has not yet eclipsed the star. So then that is the in-time interval where we can actually see the signatures of the planet's atmosphere on the light that is measured by the telescope. So this is really cutting edge now, and many such planets and their atmospheres are being studied as we speak. I have shown just one example at the top, at the bottom right corner of this slide, where signatures of water vapor have been discovered in the atmosphere of this particular planet around a star. I will switch gears now and talk about another episode in our research and understanding of the cosmos. And this is the work of Cecilia Payne Gaposchkin. So, Payne Gaposchkin's life story is again another extraordinary one. She did an undergraduate in physics from Cambridge in England, but she decided to move to the United States because she knew that in England, because she was a woman, she would not be able to get a job doing research. She would have to only go to teaching, which would not allow her to do any research. So she decided to move to the United States and did work there studying stars and their spectra. So she accumulated uh, spectra such as these, which shows the rainbow and the dark line, the Fraunhofer lines superposed on top of that, for a very, very large number of stars. Around the same time, Meghnad Shah, working in India, had theorized what is called now the Shah equation, which was a relationship between what we see in a star, in a hot star in the cosmos, and the kind of atoms that constitute it. So basically, Meghnad Shah applied quantum physics and statistical physics to understanding stars. So, statistical physics is a branch, is an approach where the ideas of probability and statistics are applied to large collections or ensembles of particles. So, Meghna Shah applied quantum physics and statistical physics to stars, and he was able to derive this equation which relates the so-called ionization state of the star, meaning to say how much the atoms in the star are ionized, that is stripped of their electrons, and he related that state to the temperature and the pressure of the stars. So this was theoretical work which he did around the same time that Cecilia Payne-Gaposchkin was studying the spectra of stars. And then he made a visit to Harvard, where Cecilia Payne-Gaposchkin was, and they met. And as a consequence of that, she applied his theory to her data. And she was able to, by making use of this relationship between the temperature and the ionization state of the atoms, she was able to conclude that stars were made mostly of hydrogen and helium. Now, this was at that time a very, very revolutionary conclusion because using the idea of universality, people thought at that time that stars, the composition of stars was just like the rocks and stones around us. So people by then had studied the composition of the Earth's crust by using chemistry and examining what are the composition and so on. And so it was assumed that the stars have the same composition. And Cecilia Payne-Gaposchkin's work showed that that was actually not the case. So this was, in a way, a sort of contrary idea to the idea of universality of what we see. But of course, it had a reason because stars, if when people thought about it, it wasn't that surprising that the composition of stars was very different from the composition of the rocks and stones around us on Earth. So, uh, but even though she studied a huge variety of stars, a very large number of stars, some of them like our sun, but some of them not like our sun. Some of them are very different temperatures compared to the temperature of our sun, much lower, much higher, and so on. The conclusion applied to all the stars that she had studied, that they were made up mostly of hydrogen and helium. So this is an article in the American Physical Society newsletter, which recalled this very, very interesting time. And initially, her PhD thesis was actually not accepted. The conclusion that she came to was not accepted by her committee members. They felt she had made a mistake. She felt pressure to actually include a statement in her thesis that her result could be an artifact of the data. But later on, luckily not too much later on, her result was confirmed by other people's calculations and works, and so the revolutionary nature of her conclusion was acknowledged. And one of the famous astronomers at that time, Otto Struve, described her thesis as the most brilliant PhD thesis ever written in astronomy. I'll switch gears now and come to the center of our own Milky Way. So, our Milky Way, as you know, is a collection of several hundred billion stars, and these stars are held together by gravity, and they make a shape which looks like a sort of double saucer kind of shape, which is known as a spiral galaxy. We, of course, don't see it that way because we are inside the Milky Way. So the Milky Way looks like a band across the sky. And in this slide, this is a slide of the photograph of the sky, which shows the Milky Way taken from Ladakh. And by the yellow circle and the arrow, I have indicated the physical center of the Milky Way. So the physical center is very close to something called Sagittarius A teapot, which is a constellation of stars roughly shaped like a teapot. And the center of our Milky Way is close to the spout of the teapot. And I want to describe to you a study of this center of the Milky Way, which was done using an infrared telescope located in Hawaii. So, starting in the mid 1990s, there were two teams of astrophysicists, one team located in the University of California, Los Angeles, another located in Germany, that was studying the center of the Milky Way because it was beginning to become clear that in the center of the Milky Way was something extremely massive or extremely heavy, and people didn't know quite what that was. And so um, the team in California was led by Andrea Ghez, and that team, she used this uh, telescope called the Keck telescope in Hawaii, which has a 10-meter sized mirror. And the telescope is located at a very high altitude, exceeding 4,000 meters. And the reason for this is because at that altitude, the atmosphere of the Earth is extremely stable. And so the images that one gets are extremely sharp. But in addition, this telescope was designed to get even sharper images, and I'll just describe how. So she set out to look at the center of the Milky Way using this telescope. And the telescope is not a single mirror, it is a collection of mirrors that are held together, each mirror hexagonal shaped, and each of those hexagons being controllable. So the point here is that what is shown in this cartoon here is that our atmosphere is quite unstable, and therefore a ray of light, if we can think of a ray of light coming from the cosmos, as it passes through the atmosphere, will be jiggled here and there. And as a result, the image that we get is limited in its sharpness. But what a telescope like this can do is, since it is a very large mirror but made up of these smaller hexagonal mirrors, and since each hexagon is independently controllable, what they do is they send out a laser beam from the telescope into the atmosphere and measure the distortions that the atmosphere causes. And then each of these mirror segments is corrected to compensate for those distortions. So this is done at a very, very fast pace with the electronics and mechanical system. And it is called adaptive optics. And what is shown here is an image of Uranus, which is somewhat fuzzy. And then once they use this technique of adaptive optics, they get a much sharper image because they're correcting for the distortions of the atmosphere. So Andrea Ghez used this piece of equipment to look at the center of the Milky Way. And she did that starting 1995, and that imaging continues even to this day. So I want to show you the result which her laboratory produced. So what we are seeing here is actually real data. So each of these multicolored splotches is a star in the center of the Milky Way. You can also see a cross, but that cross is not real data, it's just representing something which you will see in a minute. So each of these multicolored splotches represents a star. They imaged all these stars and they kept imaging them at different times, starting 1995. And so on the top right-hand corner, you can see the date in which each of these images were taken. And all of these images were put together to make an animation so that we can see how these stars move. And that's what I'm showing you here. So you can see the stars moving now, and you can see dashed curves which are meant to guide your eye as to the path that these stars are taking. And what is clear from this animation, which is real data, it's a collection of real data starting 1995 and ending in 2022, is that these stars are not moving in straight lines. They are not moving randomly. They are moving in elliptical orbits. We again see the principle of universality playing out here, because this is very, very reminiscent of our own solar system, where the planets are moving in elliptical orbits around the sun. But the difference here is that all these, first of all, it's not planets, but these are stars which are moving around a certain point in the sky. That point is what is marked by this cross. And what we see is all the elliptical orbits have the same focus located on that cross, which means that there is something very heavy located at the cross, which is driving all these stars into elliptical orbits. But also, we don't see any emission from that heavy object. So it's a dark object. Furthermore, if you look at the closest star, which is shown by this yellow orbit, yellow track, this star comes very, very close to this cross, but then it continues along its elliptical orbit. So there is no evidence of any kind of collision or deflection of its orbit or anything. What that means is that the heavy object that is driving these stars in elliptical orbits has to be smaller than the closest approach to that dark object of this closest star. So you get an upper limit on the size, and we can calculate the mass. And it turns out that the mass is 4 million times the mass of our sun. And if that much mass has to be in a radius that is smaller than the closest approach of this star, it means that it's got to be a very, very compact object. Indeed, it has got to be a black hole. So this was the first direct evidence that there is a giant black hole that is 4 million times the mass of our sun in the center of our Milky Way. This discovery got both the scientist groups the Nobel Prize in Physics in 2020. So I want to end by showing you this real image of a very, very tiny piece of sky. So this is an image of a piece of sky that is 1/10 the size of the moon, which is what I've shown in the corner over there. 1/10 the size of the moon on the sky. So not 1/10 the physical size of the moon, but 1/10 the size of how large the moon appears on the sky. And there are thousands of galaxies in this image. There are some stars which look like crosses and can be easily identified. So, for example, you see one a little bit below the center of this image, one to the top right of the center of the image, and so on. But other than those, every dot and smudge on this image is actually a galaxy like our own Milky Way with hundreds of billions of stars. And so, again, we see this universality play out. Our Milky Way is very, very unexceptional, very ordinary. There are thousands, billions of galaxies like our Milky Way all across. This image has thousands, but this is such a small piece of the sky. So when you know that this extends to the whole sky, the whole cosmos, you can imagine the number of galaxies there, the number of stars in them. And so the 10,000 galaxies or so in just this image, each has a giant black hole in its center. Each has hundreds of billions of stars. Each star likely has a planetary system around it. And each of those planetary systems has a potential to harbor life. So I'll stop there. And if you have any questions, I'll take them.
Thank you, Prajwal, for a very enlightening and very exciting narration of many things that Bruno imagined, but now we find that those basic points that he imagined are being borne out by the latest developments in observational astronomy. So now we have got about 15 minutes for a question answer or comments. Anybody who would like to ask a question, please raise a hand. Okay, Mohana ji, please turn on your mic and ask your question.
Yeah, I listened Prijwal Sastri's speech for the first half an hour when you introduced her. It is an excellent work, but I want to know how anybody, those who want to study astronomy like her, can that person or student can proceed in the way to study about the black hole or to study about that stars. How can that person can continue after getting the graduation in physics or mathematics?
Thank you,
Okay,
Mohandas.
Prajwal,
And
Prajwal,
after that,
before
I
answering
will
that question,
raise one question.
Prajwal,
Being the
before
zoologist,
answering that question,
okay,
we'll take 2 or 3 questions and then you answer all of them together. Okay,
okay,
so
Okay.
we'll park this question of Mohana's.
yeah.
Any other question would anybody else like to raise?
Shall I ask one more question?
Yes, yes. Go ahead.
Today is a Galileo's birthday. That we have to think and thank a lot for him for the discovery of so many astronomical materials. But I saw the slides which was shown by Prajwal Sastry. Did she see these galaxies, any one of the galaxies, through the telescope or anything else? Did she see it? Or did she study it and convey it? Let me know this. But another thing, there is one question is going on. There is a habitual planet will be there anywhere in any other galaxies. Was it found like this? Was it known any new habitatory planet in any of the near galaxies? Or let me know this. Only 3 questions. Thank you.
So can I, this is Balu here from Pondicherry. Can you hear me?
Yeah, please ask a question, Babu.
Yeah, so it's completely fascinating. Thank you very much. And all these 10,000 galaxies and the possibility of life. I'm wondering what happened to all these Voyager missions that happened and where are they? What have we learned from the extra Earth explorations? How does it add to this knowledge? Thank you.
Okay. See, we have just 10 minutes now. So I think we have 3 questions from Mohanaji and 1 question from Balu. All of them are big questions. So I will request Prajwal to please respond to these questions which have been raised. Prajwal ji?
Yeah, so the first question was about doing research in astrophysics. So after BSc, I would recommend that the students look for a master's program in physics, which has good teachers and good laboratories. Physics is the basis of astrophysics, so it's really important to have a solid physics understanding. And once that is done, then uh, it's one the student would be suitable to apply for PhD programs, or even if not PhD programs, then apply for research positions after a master's in any astrophysics laboratory. So that is what I would recommend. I would not recommend a student to want to study black holes or whatever. But I mean, there are many, many things to study in the cosmos, and black holes are just one of them. The students should just reserve their judgment, keep an open mind, and see what is interesting. It's also important to have people who are good teachers and good mentors, so those should also be factors in deciding what field to pursue, and the kind of institute and so on. And so that's what I would recommend. The second question was I didn't write these questions down, but I think the second question was whether I have observed any of these galaxies myself. Well, the Milky Way is something we can see with our naked eyes. Um, we meaning we as citizens have now polluted our skies very heavily with light, with a lot of unnecessary light. So it's more and more difficult to see the Milky Way. When I was growing up, I could see it from my garden. We used to spread a mat on the garden in the garden and watch the sky, and we could see the Milky Way. Now you have to go to distant villages and remote areas in order to see it, but it is really something that should be seen at least once by everybody. So we can see that with our naked eyes. We don't need a telescope for that. So I've seen the Milky Way many times, and I have seen galaxies as well through the telescope. Maybe not the particular galaxy that I showed you in the slide. I don't recall actually, but probably not. But there are many galaxies that can be seen which are much nearer than the kind of galaxies that I showed in the slide, and they can be seen in great detail through the telescope. And I kind of forgot what the third question was that Mohana asked.
Habitual planet in the near galaxies.
Yeah.
Yeah.
So, habitable planets is a phrase that scientists tend to use to describe a particular kind of planet. I personally actually don't like that phrase, and I'll tell you why. So, a lot of planets have been discovered, like I said, thousands of them. Some of them are at a certain distance from their star, so that their temperature is such that water can exist in liquid form. So the Earth, because of the distance that the Earth is from our sun, and because of the kind of brightness our sun uh, radiates at, water can exist in liquid form at room temperature. So there are similar planets among the collection of planets that we know, which are also at such distances from their sun. So most planets are either very close to their sun, so the temperatures are too hot for water to exist in liquid form, or they are very far away, so that the temperatures are too low for water to exist in liquid form. But there are some planets where water can exist in liquid form. They are just at the right distance from their own star for that to happen. And there is a tendency among scientists to call them habitable planets. I don't agree. I don't like that term for two reasons. One, by saying it is habitable, what we really mean is that in order for human beings to survive, and therefore in order for life like what we know it to survive, uh, water needs to exist in liquid form, which is true, but we really don't know what life is. We don't have a good understanding of what life is. So it could well be that there are other forms of life which do not need water to exist in liquid form in order to exist. So that is one point. But the second point, and maybe more important point, is that uh, somehow I feel that by calling these planets habitable, there is sort of a message that human beings can create a big mess on the Earth, and then we can all pack our bags and go to a different planet to live there. And that is not correct. That will never happen. All of these planets are more than 26,000 light years away. The center of our Milky Way itself is 26,000 light years away. All the planets that I've discovered so far are thousands of light years away, which means light takes thousands of years to get there. So there's no way human beings can get there. I mean, even to get to Mars is $1 trillion project, and it's not going to happen. So I think it is disingenuous to call these planets as habitable planets because it's giving the wrong message. Balu's question, what are the insights we have got from space exploration? It's a very good question. And basically, from these explorations, we have learned about the planets in our own solar system because they have I mean, it's very, very difficult to cross these vast distances from Earth, right? So the nearest star to us is 4.5 light years away. So there is no space mission that has reached that far. There are a couple of space missions which have gone beyond the solar system. But mainly, what we have learned from them is as they pass very close to cosmic objects in our solar system, such as planets and also comets and asteroids, we have been able to image these things with great detail and learn more about them, what they consist of, how their surfaces are structured, what is the composition, etc.
Thank you,
Okay,
Prajal.
I think
Thank
we
you
are
so
very
much.
close to 7:15, and we have decided to conclude this session by 7:15 because there's some meetings after that. So I think we will adjourn the question and answer session here. And I will just, in 1 minute, there is a question from Nitya. Okay, Nitya, go ahead. Last question.
Thank you, sir. Really a wonderful session. We enjoyed and enlightened this Sunday evening, sir. Thank you, ma'am. Thank you, ASPN. Ma'am, I wish to know whether the hypothesis of multiverse is real and how the research is going toward that concept. And I also want to know what's your opinion about this multiverse concept, whether any possibility of the existence.
Okay, so I don't work in that area, so I can't actually answer your question. Uh, there is no empirical evidence for multiverses so far. So they are multiverse. The idea of multiverse is in the realm of speculation. But I don't work in that area, so I wouldn't be able to say whether, I don't have an opinion, shall I say. I will have an opinion when there is empirical evidence, but right now I don't have an opinion.
Okay, thank you very much, Prajwal. I'm sure there are, many more questions which people, participants here would like to ask. And unfortunately, we have come to the end of the time slot. I would like to conclude with one more piece of information about Prajwal ji, which I did not share in the beginning. And that is that Prajwal ji is also one of the vice presidents of the All India People Science Network, ECs. Am I correct, Prajwal?
Yeah.
Yeah, well, that is, I think, very relevant. And we're very happy and proud of the fact that one of our vice presidents has spoken so authoritatively and so interestingly and so understandably about some very complex things. I'd like to conclude by inviting everybody here to become part of the next part of our observation of Giordano Bruno commemoration, which is the day after tomorrow, where Dr. Priya Hassan will be speaking again on astronomy and some learnings from the very large telescopes. So we will conclude here with thanks to Prajwal ji, thanks to the organizers, thanks to all the participants, and see you again the day after tomorrow. Thank you very much.
Thanks to the chair, Vivekda. Thank you for nicely conducting the session.
Thank you. Thank you so much for everybody who has coordinated for this. Thank you, Anubaji. Fine.
Okay, we will conclude here. Thank you.
Thank you. Good night.
Good night.
Thank you. Thank you, everyone. Good night.
Thank you. Thank you, everybody. Good night.